So in this video, I want to talk about what's called the Sieve of Eratosthenes. And before we do that, I want to talk about the following proposition. And so it turns out if you want to determine whether some integer is a prime, let's say you want to run a computer program and you want to determine whether or not, say, 103 is prime. Okay, so determine whether or not 103 is prime. It turns out, for good reasons, what you can do is you only have to check all the primes up to a square root of 103. So square root of 103 is like 10 point something, I don't care, 10 point whatever. So all you really have to do is check, does 2, 3, 5, or 7 divide 103? And you can check right away that 2 does not divide 103, 3 doesn't divide 103, 5 doesn't divide 103, 7 doesn't divide 103. You can check all those, and therefore 103 is prime. So 103 is prime. And so this process is actually called the Sieve of Eratosthenes, and I want to explain the math of what's going on here. So I'm going to word this in a proposition. If n is an integer greater than or equal to 2 and it's composite, then n has a prime factor p. So n has a prime factor p less than or equal to square root of n. That's really what's going on there. So with our example with 103, since all the primes up to square root of n did not divide 103, we can conclude 103 is prime. All we have to do is check those 4 numbers. You don't have to check all the numbers less than or equal to 103, just those 4 numbers. And let's prove this. This is actually a corollary of a statement that we've already proved. So let me just word it this way. But this follows from the fact that if x and y are positive and x times y is greater than, say, greater than or equal to c, then x is greater than or equal to square root of c, or y is greater than or equal to square root of c. Okay, so this is the statement that this follows from, is that if you have 2 positive integers and their product is some value, say that it's at least c, then at least one of the terms has to be greater than or equal to square root of c. The proof is a proof by contradiction. If x is less than square root of c and y is less than square root of c, then x times y is less than square root of c times square root of c, which is c. And so, I'm sorry, this is not contradiction, this is the contrapositive. Contradiction can also work, but the version I just said was the contrapositive. So if x is less than square root of c and y is less than the square root of c, then xy is less than this c. So that proves the statement. The statement in turn proves the proposition, because for the proposition, you can think about what's the smallest prime factor p of some composite integer n, and if it's smallest, that means that that's got to be the one that's less than or equal to square root of n. So I will let you fill in the details there. I think this is worth thinking about exactly why that works. The write-up is written very nicely in the course notes. So I'll just leave that as it is. But let's use this to find all the primes up to, say, 50. So I'm going to use this to find the primes. And this is, again, a method that was used by a Greek mathematician, polymath named Eratosthenes. Eratosthenes was actually famous for 2 things, really. Well, most famous for 2 things. He was famous for this method of finding all the primes up to some integer. And then he was also the first to give an accurate estimate of the size of the Earth. And basically he used his knowledge of the equinox, and then he used a very sophisticated technical argument called a stick, with the sun and measured the angle that the shadow cast on the sun. And with that information alone was able to determine, literally he used a stick from a tree. And with that, he was able to determine the radius of the Earth accurate to about 8%. This was about 500 BC, 300 to 500 BC. So Eratosthenes was a cool guy. I, in fact, told my wife we were going to name our second son Eratosthenes. She objected. He's not named Eratosthenes, luckily for him. Anyways, so the Sieve of Eratosthenes works the following way. What we're going to do is we're going to start with the smallest number that we can, which is 2. So that's a prime. And then what we're going to do is we're going to cross off all the multiples of 2, and those are not going to be primes. To be clear, we're crossing off all the multiples of 2, except obviously we're leaving 2. So we're going to cross off all the multiples of 2. So those can't be primes. Okay. The next number that we're going to have is 3. And we're going to cross off all the multiples of 3 that haven't already been crossed off. And so let's see, we have 6 is gone, 9, 12, 15, 18, 21, 27, 33, 39. There should be one more. Yeah, 45. Okay, so those are all the multiples of 3. And then after that, we'll have 5. And for 5, let's see, all the multiples of 5 that haven't been crossed off, all the 10, 20, 30, 40 are gone. So I think the only one that we're missing now is, oh, we're missing 2, 25 and 35 haven't been crossed off yet. And then finally, we can stop, by the way, I should have mentioned this. Since we're going up to 49, we can stop when we get to the square root of 49. So in our case, square root of 49 is 7. So we're going to cross off all the multiples of 7 that haven't already been crossed off, if there are any. And so let's see, we'll have 7, but then we'll cross off 14. We'll cross off 21 is gone, 28, 35, 42, and 49. I don't know why I changed colors partway through, but I did. And so the numbers that we're going to be left with are going to be 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47. Okay, and those are all the primes less than or equal to 49. Okay, so there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 primes less than or equal to 49. Okay, and there they are. This is a wildly inefficient method to find all the primes up to some value, but it's not that inefficient. So there's some modern day faster algorithms that are just a little bit faster than this, but this is not the fastest way anymore.